Hi and welcome to C.3 Wave Phenomena. There's quite a lot in this topic actually and heavily assessed in exams. Particularly you're looking at the assessment of the double slits. So actively revise, actively study with me. Standard level students will study the learning objectives shown on this slide. It will take, about 40 minutes for us to go through this. Now, we'll all start off, standard and higher level, looking at the difference between wavefronts and ray diagrams. We touched on it in C2, the wave model. Let's take it a little bit further in C3 Wave Phenomena. Here we have in the top diagram here, we have a bird's eye view of, say, a ripple tank. And hopefully you've been shown a ripple tank in class. So we have the ripple tank from above here. And you can see the darker lines are the troughs of the wave. So the darker lines are these. And the lighter lines are the crests of the wave. And if you were to represent this real life situation in the ripple tank in a diagram, what you would do is you draw a wavefront diagram. And it's basically lines showing the crests of a wave. A wavefront diagram basically illustrates the arrangement of the wave's crests as they travel. And the wavefront diagram can be quite useful when you are looking at refraction. Conversely, you may see something called a ray diagram. And a ray diagram illustrates the movement of the energy as the wave travels. So instead of drawing all the wavefronts, because let's be honest, that's a lot of work, we just draw one line with an arrow on the end that shows the direction of the energy travel. And again, this will become more clear when we look at reflection diagrams, refraction diagrams. But for the meantime, let's just be aware that you can represent waves using a wavefront diagram or a ray diagram. Now for this, you're going to need four things. You're going to need a pencil, a ruler, a protractor, and a rubber. And if you don't take those four things into an exam, you will be at a disadvantage. Here we are straight in to a diagram showing the reflection of a wave. And what this diagram is actually doing is showing two types of diagrams. It's showing a ray diagram and it's showing the wavefront diagram. And remember that the wavefront represents the crests of the wave, how they travel. Let's have a look at the wavefront diagram first. You can see that the incident wave, the wave that comes towards the boundary, is angled, it's about 45 degrees. The incident angle is equal to the reflected angle. And what do I mean by that? Well, if we draw something called a normal, you've come across a normal before, I'm sure. It's a straight line that is at 90 degrees to the boundary, and you always measure your angles from that straight line. So the incident angle is the angle that the ray makes with the normal. So that would be 45 degrees, that's the incident angle. And therefore the reflected angle would be 45 degrees. Now our diagram's getting a little bit messy, so let's try and put it to the side. We've got our boundary here. And in this case, we're assuming that nothing's transmitted, nothing's absorbed, everything's reflected off. We draw our normal at right angles to the boundary. You have an instant angle coming in, and that's where it hits the boundary, and that's our instant angle. And it reflects exactly the same angle it came in at. It reflects at the same angle. I equals R. And that's the basic law of reflection. We'll start by looking at diffraction from a purely conceptual point of view. That means we'll just find out what diffraction is, note a few interesting points about it, and that's basically all we need to know for standard level. Later on in this tutorial, if you're a higher level student, we'll delve into a little bit more of a mathematical approach to diffraction. But right now, what is diffraction? Well, diffraction is when wavefronts change shape when they pass through a slit or around an edge. And in this screen here, you can see we have a slit. This is a slit. The wavefronts approach that slit, and after they pass through the slit,
you can see that they've changed shape. They've curved round a little bit. And that curving of the wavefronts means that the energy has spread out. One of the things that's notable about the slit, or the gap size through which these wavefronts move, is the size of the gap has a really big effect on how much those waves will bend or spread out. And you can see we've got 3 situations here. Let's label them 1, 2, and 3. Situation 1 is where we have a relatively large gap in comparison to the wavelength. In fact, you can see that the gap size is larger than the wavelength of the wave. And the wavelength, of course, is the distance between each wavefront. When that happens, the wave doesn't diffract very much at all. You can see there's very little curvature. Situation 2 is where the wavelength is roughly equal to the size of the gap. You can see that the wavelength is about that size and the gap is roughly the same. This is where we get maximum diffraction. If we want the biggest spreading out of waves, we want the gap size to be similar to the wavelength of the wave. And the final situation we have is where the wavelength is much greater than the gap size. That's situation 3. We still get the curved wavelength fronts, but the wave doesn't spread out as far on these sides here. So we still get the curved wavefronts, but it doesn't spread out as far. As we found in situation 2 in the previous slide, maximum diffraction is experienced when the wavelength is a similar size to the gap. It's not just a gap that waves can bend around, and it's not just a gap that causes diffraction. In fact, when any waves meet any obstacle, they can start to bend around the object. As shown in this slide here, we can see that the waves are now travelling left to right, and as soon as they hit the obstacle, we can see after that obstacle they start to curve round. And that curving of the waves is due to diffraction as well. Let's have a look at how that occurs in real life. First of all, we'll look at diffraction through a slit. If you've ever been to a harbour where people would tend to moor their boats, then you'll notice that the harbour walls are very cleverly engineered to ensure that any large waves from the sea are spread out. And why would they want these waves to be spread out? Well, we want the energy to dissipate. We want the energy inside the harbour to be lower, which means we don't want waves that are as big. So if we can spread the waves out, the energy gets spread out and the waves are lower inside the harbour. Another example of diffraction in real life is actually probably not so relevant in this day and age, given that we get most of our television and radio via the internet. But if your household receives any radio signals, either via television or radio itself, or perhaps you live in a very hilly area or remote area where there are no internet cables, then you will rely on waves to reach you from a transmitter to a receiver in your house. And of course, things like hills will cause waves to diffract. If the television program you're watching has a very high frequency, that means that the wavelength is very small. Can you see these very small red wavelengths? A small wavelength and a large obstacle means that the diffraction doesn't happen as much. So if your house is behind a hill and you're listening to a high frequency radio station, it's highly unlikely that you will receive that station. If you choose a lower frequency radio station, then the lower frequency radio waves have a longer wavelengths. It's easier for them to bend around the obstacle, and you're more likely to receive the signal at the bottom of the hill. So the lesson here is, if you live in a hilly area, listen to lower frequency radio stations or watch lower frequency television stations to make sure that you can get that signal. Or of course, use a satellite and none of this becomes a problem. Haha.
In this section of the tutorial, we're going to look at what happens when you go from the boundary, from one medium to another. Does that mean, well, say from air to glass, or from water to glass, air to liquid? You get the idea when we're moving from one medium to another. So material interfaces, that is the fancy word for the boundary between two different materials. If you really want to be a good physicist and you really want to get top marks, then let's start using words like material interfaces or boundary. There are three things that can happen when waves arrive at a boundary. It can be reflected, it can be refracted, and it can be absorbed. Let's look at absorption just for a second. And what we have up here in the picture is Kalamata or it's not olive oil we're interested in, although I am hungry. I wonder what those spices are. They're not spices, they're herbs, aren't they? Oh, I wonder if it's basil. Oh, yummy. Anyway, that's not physics, is it, folks? I'm interested in the microwave. What a microwave does is it uses a special type of wave from the electromagnetic spectrum. Can you guess what wave from the electromagnetic spectrum it uses? Yes, it's a microwave. And those microwaves are released from the microwave. This is confusing, isn't it? Inside the microwave. What happens is a special pattern is set up by those microwaves, by them being released and bouncing back on themselves. And this pattern is called a standing wave. And a standing wave of those microwaves is used to cook food. So let's pretend you've got a big plate here of spaghetti bolognese. And the microwaves transfer energy into the material's energy store. So the microwave transfers energy into the spaghetti bolognese. Spaghetti bolognese. In the form of thermal energy. We talked about the three things that can happen when a wave meets a material interface. The second thing is refraction. Refraction is when waves are transmitted to the next medium and change speed and direction. I'd like to now look at what happens when light waves arrive at a boundary between two different materials. When a ray of light is incident on the boundary of media of different optical density, so this is more dense, say this is glass, than air. Most of the light transmits, so you can see most of the light here is transmitted. It's gone through, but we're not going to use the word gone through because we're physicists now, so we're going to say it transmits. And at this point, it changes speed. Some of it is reflected and doesn't change speed, it's got the same speed. This is known as refraction. This part here is known as refraction. So let's look at that in more detail. We've got the more dense object here and the less dense up here. And what you can see is when light enters a more dense medium, the speed decreases, it gets slower. The wavelength decreases, but the frequency stays the same. Let's have a look at this in a little bit more detail. You can see there's wavefronts here. It's a wavefront diagram, so that shows the crests of the wave. You can see that as it meets the medium, let's have a look at this wavefront for example. As each part of the wave or the wavefront meets the medium, it instantly slows down. And what that has the effect of is it bends the wavefront and ultimately bends the direction of the wave. So when a light ray hits a more optically dense substance, it bends. And what way does it bend? Well, let's draw a normal. That's a normal line. Remember, the normal line is perpendicular to the interface. Then you can see that the light bends towards the normal. When a light ray enters a more optically dense medium, the light ray bends towards the normal. I'm going to look at the same diagram, but this time I'm looking at this section here where the big arrow is. This section here is where it's a more dense medium travelling into a less dense medium. So we've got density, And this is optical density. So we looked at this side earlier and we said these things happened. Now if we go to a less dense medium, we see that the speed increases, the wavelength increases, and it bends away from the normal. Let me just show you that. Here's our normal. You can see the angle here, angle of incidence here, is much smaller than the angle of refraction there, and it's actually bending away from the normal. When it goes into a less dense, it bends away from the normal. But guess what, folks? What happens to the frequency? Say it with me. It always stays the same. It always stays the same. It always stays the same. Here's an interesting exception to the rule. Can you see, if I was to draw a normal here, oh, the normal is the ray, isn't it? And what happens when light rays enter a more optically dense or less optically dense medium along the normal? It doesn't change direction, but all the same stuff happens. Let's do this one more time. The only difference with this is because it's travelling through the normal into these different material interfaces, is it doesn't change direction. Refraction in real life. Have you ever tried to catch a fish with an arrow? It's not that I have ever tried to catch a fish with an arrow. I haven't. But I have tried to catch a fish with a small net with my children, and it's frustratingly difficult. And the reason it's frustratingly difficult is because you see the fish, because our eyes think we see in straight lines, right? So the actual fish is here, but the water refracts it. So there's our normal. The light ray enters a less dense, so a less optically dense material when it travels into air. So it bends away from the normal. The actual fish light rays reach us through a bended path. But our eyes are not clever enough and our brains are not clever enough to realise that. So our brains think that actually it's in a straight line. So when you're trying to catch that fish, you're actually aiming at the wrong part of the water. Try explaining that to a 3-year-old. That's not easy. In real life, if you try and catch a fish, refraction will not be your friend. But where refraction will be your friend is if you can't see very well and you have to wear glasses. Because what glasses do is they have lenses. And lenses refract the light so that the images that you are trying to see are focused at the correct point. And the correct point is here. So we come to our revision notes, and I'd like you to draw the common diagram of refraction. When light enters a different medium with a different optical density, it changes speed, and we've seen that before. I'm just drawing a normal line here. So for example, if light enters glass at a certain angle, and this angle is the angle of incidence, it changes speed, it slows down, and what that does is it causes it to bend like that. And how much it bends is determined by something called the refractive index. It's not determined by the refractive index, it's measured by the refractive index. And the refractive index is just a number. And interestingly, and we'll talk about this again later, it's a number between 1 and around about 2.6. And if you get an answer for the refractive index that's outside of this range, then it's probably wrong. And this is for light only we're looking at here. The refractive index N of a medium, and a medium is something with an optical density, so in this case the medium would be glass is defined as the ratio of velocity of light in a vacuum. So let's write this out, is the ratio of the velocity of light in a vacuum, C, VC, to its velocity in a specified medium, VM. So that's how we define the refractive index. The speed of light is always largest in a vacuum. So if we're looking here and we've got a vacuum here, and for the purposes of life, let's just say that an air is similar to a vacuum, then the speed of light in a vacuum is 3 times 10 to the 8 meters per second. So if you were to have, looking at the speed of light in a vacuum, then the refractive index has to always be greater than 1. Well, the angle that the amount of light changes is directly related to the speed. And actually, what we can say is N, as we said before, is VC over VM. But a little bit of maths also tells us that it's sine I over sine R. I is the angle of incidence, and that is where the light is incident on the medium change or the medium boundary, so that's our angle of incidence there. And again, the angle of incidence is always between the light ray and the normal. Okay, it's not this bit here. No thanks. We'll get rid of that so you don't remember that. The angle of incidence is always between the normal and the light ray. And that's the sine function that you should be familiar with. This angle of incidence I is always going to be between, it's going to be greater than 0 and less than 90, isn't it? Because this value here is 90. So your angle of incidence is going to be between 0 and 90. R is the refracted angle. And you can see once it's gone past the boundary, you can see that there's still the normal here. And there's a light ray close to it. This angle here is the angle of refraction, or the refracted angle. And again, it's between the light ray and the normal. You're also going to notice that you can use this as well. Because if you look at V equals F lambda, if V increases, lambda increases, V and speed and wavelength change at the same rate, or have the same ratio change, because frequency never changes. It's a constant for light if you're using one particular colour of light. So V and lambda are directly proportional, so you could also have your equation looking a bit like that. This graph is going to allow you to find what the refractive index of the glass is. You plot sine R on the x-axis, you plot sine I on the y-axis, and let's just rearrange things for you slightly. N equals sine I over sine R. So that means that sine I equals N sine R. And I want you to think about the equation of a straight line. Okay? C is the y-intercept. And you can see in this graph that the y-intercept is 0. So y equals mx, and if we relate y equals mx to what's given here, on the y-axis we've got sine I, on the x-axis we've got sine R. That means that our gradient is equal to n. So if you calculate the value of gradient of this graph, the value of gradient, the number, will give us the refractive index. And that value of the gradient, or the number of the refractive index, will be between 1 and 2.6. The reason I give a value of around 2.6 is that the refractive index of diamond, which is one of the most optically dense substances, is 2.42, I think. So it would be unusual for you to be examined anything greater than diamond. Now, why would we draw a graph rather than just saying, okay, I want to find out what the refractive index is, so I'm going to do sine I, take a number and divide the number? Well, that
calculation could be wrong. It could be an outlier. It could be an error. And in which case, if that was an error, then your point of your graph would sit far away from the line. So if you do it lots of times and you get a nice straight line with all the points on the straight line, you know that your experiment is reliable. So that's why we use a graph to calculate n instead of just using the formula. So n equals sine I over sine r. You might also want to write n equals Vc over Vm. And I'd also, in the common graph section, draw sine r, sine I, and have your gradient is equal to n.
We're now going to look at something to do with refraction that makes refraction really useful. And that is something called total internal reflection. There's a process where total internal reflection takes place, and that kind of means that it keeps the light inside a piece of glass. And if we can keep light inside a piece of glass and cause it to travel down that piece of glass, that allows us to send signals. So let's think about the limit of refraction. Previously, what we've talked about is we've looked at glass and air. We've got our normal like that. And we've had light travel down to a boundary from air into glass, and it's bent towards the normal as it slowed down and entered the glass. I'd like to think about it in other ways now, so let's go down to this diagram down here. I'd like the instant ray to be inside the glass now, and the glass light ray, or the light ray inside the glass, heads toward the boundary. And at this boundary here, that light ray speeds up. And by speeding up, it bends away from the normal. And you can see the refracted ray here has bent away from the normal. So that's what happens when light goes from a media that's more dense into a second media that is less dense. The light refracts away from the normal. But let's say we have our instant ray a bit wider. So this instant angle is a bit wider. It's going to get closer to this boundary, isn't it? And eventually you're going to get to a stage where the instant angle, and we'll label this C, causes light to refract and bend along the boundary between the two media. And that's what I mean by when I say the angle of refraction will eventually approach right angles. So at this stage here, we call that the critical angle. It's critical because it's a critical point between it being refracted out here, or refracted back in, which is in here. The critical angle. And the definition of the critical angle is the angle of instance that causes the light to refract out along the boundary between two media. I suggest that's quite a good definition for you to memorise, and I'd pop that in your definition section of your notes right now. And you can see that when we look at the critical angle, and it's shown in this diagram here, the refracted angle is 90 degrees. The incident angle is not I, it's theta C. So it's well, some people call it theta C, some people just call it C, but that's the critical angle there. There are special conditions. The light must always travel from a more optically dense medium into a less optically dense medium. What does that mean? Well, this situation here wouldn't work if this was air and that was glass. It has to be the other way around. It has to be that the light is already in something that's more dense and travelling to something that's less dense. When the less dense medium is vacuum or air, the expression for the critical angle becomes. So this is the formula you should be able to use. N1 or N is the refractive index. You'll always be given that. Well, you might have to work it out, but you'll be given everything you need. And theta C, or sometimes written as sine C, is the sine of the critical angle. Don't be afraid of this expression. It's not hard. It's simply popping in numbers and rearranging. And for instant angles smaller than the critical angle, so let's go back. So let's say we're looking at instant angles that are smaller than the critical angle, like that, there will always be a very low energy reflected rate within the medium. So most of the light will come out and refract away from the normal, as we talked about before. But there will always be a small amount of reflected ray, very low intensity, that reflects inside the boundary. And that's just something to be aware of. We're going to look at what happens when we go above the critical angle now. If our critical angle is here, that's our critical angle. And as we go through the critical angle, it refracts along the boundary. If we make our instant angle greater than the critical angle, what happens is all of the light is reflected internally, and the angle that is reflected by is the same angle that is instant on the boundary. Let's go over these 2 points. When the angle of instance is greater than the critical angle, the light does not refract out of the medium, so it doesn't come out here like it used to. Instead, all of the light is reflected back into the original medium. And that's how periscopes work. Periscopes in submarines make use of total internal reflection. If you imagine you're a man down here inside a submarine, we'd have a prism that you have set up in 2 separate ways. You've got prism 1, prism 2. The light from the ship enters the prism at right angles, so it doesn't change direction. It's internally reflected, so the angle of instance is greater than the critical angle, so it reflects down. It travels out of the prism because it's at right angles, travels out without changing direction, hits the next prism, travels straight in without changing direction because it's along the normal, and it hits the boundary at an angle greater than the critical angle, and then it reflects back out into the eye. So what we can assume from this situation is that the critical angle must be less than 45 degrees, because the way that this triangle is set up, this angle here is 45 degrees. So if we're hitting the light at 45 degrees, it's got to be greater than the critical angle, so the critical angle must be less than 45 degrees for it to totally internally reflect. Other uses of total internal reflection are optical fibres. So we use optical fibres to transmit information, and that information can be broadband signals, it can be signals inside of somebody's body, it can be cameras inside people's bodies. We use optical fibres at all times, and we also use them to make things pretty. You can see this lovely optical fibre lamp here on the side uses this exact setup to show this beautiful light coming at the end of the optical fibre. Let me talk you through it. Light rays approach the boundary at angles greater than critical angle. So what we have here is we have a high density fibre, and here is a low density fibre. So it's going from high density to low density. So total internal reflection can take place. It hits the boundary, that's the boundary there, at an angle that is greater than the critical angle, so it reflects at exactly the same angle out again. Then it travels down the optical fibre slightly and it hits the boundary again, just depending on how bendy this optical fibre is. And again, it hits the boundary at an angle which is greater than the critical angle, and it reflects exactly the same angle. And it does it again and again and again and again and again and again and again until it comes out the other end and passes information on to somebody else. So what would we use optical fibres for? Well, I mentioned it before. We'd use it for computer data, telephone calls, and what we do with that is it converts digital signals of electromagnetic waves into whatever we need it to be. And those signals are carried as light waves or light pulses through optical fibres. So the internet, phone, they all use optical fibres. They're good for a number of reasons. They allow us to send information over very long distances. As long as you've got the cable is the distance you can send the signal. And that's different from sending it through the air, because through the air, your signal will die off over time. And it has to be redirected as well because the Earth is round. Sorry to all you flat earthers, but the Earth is round, so your signal has to be redirected. But with an optical fibre, as long as you've got a long cable, that signal will get there no problem. They can carry more information than satellites. There's not as much energy loss. And actually, it's more secure. It's more unlikely for somebody to hack into your optical fibre than it is to be able to pick up a signal from a transmitter or a satellite. Another use of an optical fibre is endoscopes. So say you want to perform keyhole surgery, then what you need is one fibre that sends light into the body, and that lights up what you're doing, and another fibre to be able to see what you're doing. So the optical fibre then sends that light back up to your eye. And going down the tube with those fibres are, whatever implements are needed to perform surgery on your lung or your lymph nodes and things like that. So endoscopes use optical fibres as well. They are used as a flexible tube with a light and a camera, and your doctor can view pictures of your digestive tract on a colour TV monitor. So they watch the TV and cut up your insides. Why would we want to use an endoscope instead of good old-fashioned surgery where they would make an incision in your body? Well, it's less invasive. Means it's not as invasive. It's not as scary. There's less chance of infection because as soon as you open up a body, there's a chance that infection can get into there. That means your recovery is quicker because there's no physical scars to heal and you won't get an infection, or you're less likely to get an infection. There's a flexibility as long as you have a channel for this endoscope to go down or up, then there's a flexibility to travel deeper within the body than surgery would offer. You can do that on one day in the hospital. You don't have to stay in hospital for days on end, and it's not as expensive. So the benefits of using endoscopes are much, much greater than having a traditional surgery where your body is cut open. So, a couple of things we want to do. I want you to go to the formulae section of your revision notes and write down our formulae, sin C equals 1 over n. I'd like you to take a couple of examples and go into your other notes section and explain how internal reflection is used in optical fibres and prisms.
It's important that we understand the terms constructive interference and destructive interference and the concept of phase difference. And here's why. Actual examiner feedback has been given saying that the concepts of phase and phase difference were a problem for many candidates. So let's put that to rest right now. We'll start with the easy stuff. This is an example of constructive interference. We have two waves here on the left. Each wave has an amplitude of 2 boxes. A1 is 2 boxes and A2 is 2 boxes. When those waves are superimposed, the amplitudes are added together. So the resultant amplitude of the resultant wave is 4 boxes. When the amplitude of the resultant wave increases, this is known as constructive interference. Destructive interference can be shown on this slide. We have the same waves here, but they're in a slightly different phase of their cycle. Amplitude A1 is -2 and amplitude A2 is +2. When these two waves are superimposed and added together, at all stages the amplitudes add to 0. This is known as total destructive interference. And in any case where the amplitude is less, it is known as destructive interference. Let's link this into the idea of phase and phase difference now. We'll go back to constructive interference here. One complete cycle of a wave, so from here all the way around up to here, can be described as 2 pi. So 1/2 of a wave is pi. 1/4 of a wave is pi over 2. The phase difference
between that wave and this wave can be given in terms of the stage of the cycle. And we can see that there's no phase difference between this wave and this wave. They're both at exactly the same stage in their cycle. So the phase difference of these two waves is either 0, because they're at exactly the same stage of the cycle, or 2 pi, or 4 pi, or 6 pi, a multiple of the phase. And the phase difference of 0 or 2 pi gives constructive interference, as we saw before. So when waves are described as in phase, it produces constructive interference. Let's go back to this idea of destructive interference, and we're comfortable with this picture already. This time, however, the two waves are not in the same phase. This wave is either half a wavelength ahead or half a wavelength behind the wave below. That means that their phase difference is half a wavelength. Now, we don't quote phase difference in terms of wavelength, we quote phase difference in terms of the cycle. So half a wavelength is known as pi, which is half of 2 pi. When out of phase waves are described, it means that they are undergoing destructive interference. We've got phase difference in our heads. The other really important concept is the idea of coherence. Interference can only take place when the waves that pass through the two slits are coherent. Now, what does coherent mean? I'll give you a real big tip here. The definition of coherent is extremely important. Please make sure you learn it. But coherent sources or coherent waves are waves that have the same frequency, the same wavelength, the same velocity, and a constant phase difference. What it does mean is that the phase difference between the two has to stay the same. The phase difference doesn't have to be an exact number. It doesn't have to be 0 or 2 pi or pi, but it does have to stay the same at all times. So your waves, when they're coherent, would look like this. Let's add another slight difficulty to the mix. Let's now talk about path difference. What we have here is a signal generator that's attached to two loudspeakers. That means that these loudspeakers are producing coherent waves. This loudspeaker here produces a wave along here, and this loudspeaker produces a wave along there. When they meet and superimpose, the trough meets the crest, so we know that destructive interference is going to take place. However, what's notable is that this wave here from L1 has to travel much further than that wave for this superimposition to take place. And what we also know is if that is destructive interference, then this wave here must travel half a wavelength longer or a multiple of half a wavelength longer than that one. Otherwise, the waves wouldn't meet at this point of total destructive interference. So the path difference at this stage, where you find destructive interference, is a multiple of half a wavelength. Let's use this example for constructive interference as well. So we look at the same setup. We have two loudspeakers, both producing coherent waves. This loudspeaker produces a wave in that direction, this loudspeaker produces a wave in that direction, and a crest meets a crest. This means we can say that the constructive interference takes place. In order for constructive interference to take place, the phase difference must be 0, so there must be a whole multiple of one wavelength between them. Now in this case, they've met exactly halfway between the two loudspeakers. L1 has travelled a distance and L2 has travelled exactly the same distance. This means that the path difference is 0, and 0 path difference means constructive interference. However, we could have it as before, where this wave travels to here, this wave travels along and travels one wavelength
longer than that to produce another region of constructive interference. So when we're looking at constructive interference with double slits, we have a path difference of 0 or a multiple of the wavelength. If we put these two together, what we find is a pattern of areas where you have constructive interference and destructive interference. Now we are looking at sound waves at this stage, so our constructive interference would be a loud sound and our destructive interference would be a quiet sound. So in the middle we have a path difference of 0 because the waves travel exactly the same path. Then on this side we would have this wave would travel half a wavelength longer than that wave to produce a quiet sound. Then this wave would travel a whole wavelength longer than that one to produce a loud sound, and so on. So the result of two coherent waves passing through two adjacent slits or through two loudspeakers is you get regions of constructive and destructive interference in a line. And incidentally, if you were to set this up in your classroom, you would hear these noises. It is observable for you. Double slit interference. More commonly, we would look at light and interfering light. We already discussed the idea of double slit interference, and we looked at the issues of path difference and phase difference when two waves are diffracted through a double slit. Crests meets trough, and it forms a destructive interference. Crest meets crests, or trough meets troughs, and a constructive interference is formed. So we find a pattern of maxima and minima as we go along the screen. This phenomenon was discovered by a scientist called Thomas Young, and his famous experiment is called Young's double slits. Thomas Young performed this experiment with light at the beginning of the 19th century, so a really long time ago. But he didn't have lasers then, and he didn't have coherent sources. So he had to come up with a way of making light coherent before it passed through the double slit. Because of course you'll remember that this experiment only works if you have coherent sources. So he took a monochromatic light, so he took light of one colour, and placed it through a single slit to begin with. That had the effect of making the source coherent, and then he placed it through the double slit. On observing the interference pattern on a screen far away, he found this interference pattern was consistent every time he tried it. This experiment proved the existence of light as a wave, and it was pretty groundbreaking at the time. So we would take a monochromatic laser, which produces an intense beam of coherent monochromatic light. This laser is then shot through two very thin parallel slits, about 1 millimetre apart. And what we find is an interference pattern on a screen which is several metres away. The maxima fringes are the bright dots where constructive interference is taking place, and the very dark areas are where destructive interference is taking place. This setup allows us to find the wavelength of light that's been projected through the double slits. There is well, in fact, you're very lucky because in the old syllabus, the old IB syllabus, you used to have to be able to derive this equation through algebra, but that is no longer necessary. What you do need to know is how to use this formula and that it relates to the double slit interference experiment. So we have S equals lambda big D over small d. If we go back to here, S is the spacing between the fringes, so that is the spacing between the centre of the maxima or the centre of the minima. Big D is the distance from the slits to the screen. So we go back to here, that would be from there to there, that's big D. Small d is the spacing between the double slits. So let's look back to here. That distance there is small d. And finally, lambda, which is the wavelength of light, is the wavelength of this light coming out. So we can find the wavelength of any monochromatic light source simply by using this experiment. This equation will be given in your data booklet during the exam. It's important that you remember what these little symbols stand for.